Hello students, in the last session we completed the leftover part of friction and those stuff. Okay, same way we did see like 4 different cases that were related to fictitious forces. Okay, so those were the stuff that we did see in the last session. So in this session, so this will be the final session for this chapter. Okay, so in this session we will see motion of car on a level road. Okay, so when a car moves on a level road, it has to make a circular turn. Okay, so if that was the case, how should the centripetal force actually acts? Okay, so that is something that we need to see. Okay, same way we'll see like motion of car on a banked road, circular motion of car on a banked road. Okay, so banked road means it's a kind of inclined road. Okay, so we'll see those 2 cases. Fine. So with that, the entire theory part will get completed, and then we will see some extra concepts which are like contact forces and those stuff. Okay, so in this session mainly we will do like 2 important sections. Okay, so those things will be done, right? So let's see. So the first thing is like motion of car on a level road. So level road actually means the road is flat and horizontal. Okay, so in that situation, if I have to make a circular turn, so how should the centripetal force actually act on the tire? That's what we need to find. Okay, so this in this case, it should be like pretty obvious. The only part that is touching the ground is like the tire. Okay, so the frictional force which is responsible for the centripetal force should actually act between the tire and the road. Okay, so that should be like clear. Okay, so let me give you an overall understanding. Okay, so the rear wheel, which means the back wheel, will be connected to the engine. Okay, so if that was the case, so the engine will pump the power, those power will be responsible for the rotation of the tire. Okay, so it gets dragged along the surface, which will push the car forward. Okay, so the car will start accelerating forward, so the rear wheel will be responsible for the energy output. Okay, so it will push the ground backwards, in turn the car will start moving forward. So that is the function of the rear wheel. Okay, so if that was the case, then rear wheel will actually be thicker because it will get dragged along the surface, right? So obviously it will be thicker. And same way, if you look at the rear wheel, the wear and tear. Okay, so the wear and tear will be at the center of the wheel. Okay, because it is responsible for the push that is needed for the movement of the car. Okay, so that should be obvious, right? So what is the purpose of the front wheel? Obviously it is for the stability. Then the important role it actually plays is for the turning of the car. Okay, so whenever you start rotating the steering, obviously the wheel will get shifted towards either left or right depending on the steering. Okay, so let me put it this way. You are just going to make a turn towards the right. So if that was the case, you will start rotating the steering accordingly. So in that case, the wheel will start shifting towards inclining towards the right direction. Okay, so what will happen in that situation? The rear wheel, which is responsible for the forward push, okay, energy output, what it will do is it will just push the car forward. Okay, in turn the front wheel is not going to move forward, in turn it will get dragged along the right direction. Okay, so because the wheel is inclined towards the right, so there will be a drag which is responsible for the right turn of the car. Okay, so once you start dragging, you should create an imagination in this situation. So the front wheel is at an inclination towards the right. Okay, it will start dragging, right? So when it starts dragging, obviously there will be a force that is acting towards inwards. Okay, so that is the centripetal force which is responsible for the turn towards the right. Fine, so you should get an overall understanding and then like imagination towards what I'm telling you, right? So that will be responsible for the turning of the car. Okay, so once the car gets turned and it is at the required orientation, so you can obviously leave the steering. The front wheel will get aligned to that of the same of the back wheel. So in that situation, the car will start moving in the forward direction. Okay, so that's how the like frictional force is responsible for the centripetal force, right? So whatever I've told you, you should have like an overall understanding. Now we will just conceptually see with the pictorial representation that I've drawn over here, and then I'll match it with the equation. Okay, so from that I'll be able to get the frictional force that is acting on the tire and the required centripetal force, right? So we'll do all those solving, right? So this is the background understanding that you need to know. From that I'll be able to build the equation. Okay, so you'll get the equation in 2-3 steps. That is like super easy, no problem with it. So here in this case, so you are having a car, okay, right? So it is moving in a clockwise direction. Fine, so in this situation it is just going to turn towards the left. Fine, so that's the case over here. Fine, obviously here I just have to make a turn towards the left. If I will have to make a turn towards the left, obviously the front wheel will be directed towards the left direction. The rear wheel, the back wheel, will push the car forward. Okay, in turn the front wheel will start dragging along the surface, right? So because of that drag, so obviously it is like dragging along, it's like scratching along that surface. Therefore you will have a push towards the inward because it is not aligned properly, right? Obviously, the earth will start pushing it inwards, right? So you will have wear and tear along the sides in the front wheel because you are having the force is acting at certain inclination, so you'll have wear and tear along the sides. Fine. So anyway, you now you have a frictional force that is acting on the front wheel, obviously on the back wheel, because it too has to turn its direction. Okay, so you are having a frictional force that is acting between the tires, which is responsible for the required centripetal force. Okay, so here the frictional force is actually creating a required centripetal force so that it is able to make this particular turn. Okay, if the frictional force is good enough for the required centripetal force, if that was the case, then obviously the car will make that turn. Okay, so if the frictional force is less, then in that case the car will make a larger turn. Okay, so what will be the parameter that the frictional force actually depends on? So we'll see that thing. Okay, so it will actually depend on the radius, and then it will depend on the velocity with which it is going to make the turn. So from experience, we should know that if you are just moving with higher speed, if that was the case, then I'll not be able to make like sharp turn, so I'll just make a bigger turn. Okay, so that will be the case, right? So if I have like more velocity, then obviously I'll not be able to make sharp turn. The turn will be much larger. So it depends on the velocity, right? So more the velocity, I just need more space to make that particular turn, right? So once we get the equation, you will see that is the centripetal force is actually directly dependent on the velocity. We'll see those things. Fine. Okay, anyway, you should be clear with this thing that I have told you, right? So now we are ready to make the equation. Okay, so to get the equation, what should be the case? Frictional force between the tire and road. So the frictional force that is acting should be equal to that of the centripetal force. When those two things are equal, then the frictional force is good enough to balance the car, right? So here I'm just going to put the maximum frictional force between the tire and road. If the required centripetal force is less than the maximum frictional force, then obviously I'll be able to make that turn. So here I'm just going to find it for the maximum case. Okay, so if I just go beyond that particular velocity, then I will not be able to make that particular turn. I just need a bigger turn. Okay, so that's how it's going to be. Fine. So to put the equation for this particular statement, frictional force between the tire and rod. So what does the frictional force actually means? So here frictional force will be like mu s and then the normal reaction. Obviously in this case it is like a static friction, because you should be clear, the car is moving like perpendicular, I mean tangential to this particular circular path. Okay, and then I'm just giving the force at in the radius. Okay, I'm just giving the force radially. So if that was the case, obviously you do not have any movement of this car towards the inside of the circle. Okay, so with respect to the radial direction, this car is static. That's why I've put like mu s. It should be clear, I'm just moving straight, but the force is actually acting perpendicular to it. In that perpendicular direction, the car isn't moving, therefore the static comes into picture. Fine, you should get this thing. So you are having like mu s n, which is equal to the centripetal force. So for the centripetal force, I'll just plug in mv square by r. I'll just put it straight away. It should be like clear. So where m is the mass of the car, right? And then v is the velocity with which I'm just going to make that particular turn. Okay, so in this case you should be able to match it, right? So frictional force directly depends on the velocity, right? So more the velocity, then obviously I'll have to need like more the friction to balance that situation, right? If I don't have that much amount of friction between those two surfaces, or the surface is slippery, in that situation obviously the car will move away from the track. Okay, it needs like a huge radius to make that particular turn, right? Okay, so this thing has to be clear. Then mu s n will be equal to mv square r. So here I'll have to get the n, right? So this is like a simple case. I've just drawn the diagram straight away over here. So you're having a car that is going to make a turn towards the left, same situation over here. Okay, so mg is actually acting downwards, right? So do we have any other force that is acting on this car? I'll have to put that one. Yes, we do have one more forces, which is like frictional force, which is centripetal force that is actually acting towards the center. Okay, so that will be like F centripetal. Obviously this F centripetal and mg is actually perpendicular to each other, right? So normal reaction comes into picture with respect to the surface or the ground in the situation. So with respect to the ground, the part that is touching the ground is actually the tire. So the normal reaction will be perpendicular to that of the ground. So here only mg is acting downwards. This component is exactly parallel to the surface. Therefore, I will not consider this fc because this is something along the x. Okay. So normal reaction will be along the y. Therefore, mg is acting downwards. Normal reaction will be upwards. Fine. So only component here is like n and then the mg. Obviously, if you just put in n j cap and then mg minus j cap will be equal to 0 because the core isn't moving down along the earth. Okay, so it is like static with respect to this y axis. Therefore, n will be equal to mg because the net force is actually balanced. Therefore, right hand side will be like 0, right? You should get this thing right. We have done this thing multiple times in the previous session, so you shouldn't have any doubt in the stuff that I'm telling you. Okay, so n will be equal to mg. So instead of this n, I'm just going to plug in mg. So you'll have mu s mg, which will be equal to m v square divided by r, right? So now let me do the cancelling stuff. M will get cancelled out. So left over are just the same thing. You will not be able to cancel anything else. So we'll have like v, which is equal to root of mu sgr. Okay. So v will be equal to root of mu sgr, right? So with what maximum velocity I'll be able to make that particular turn. That's what this equation actually represents. Okay, so if the velocity was equal to this one, mu root of mu sgr, if the velocity with which I'm coming is equal to root of mu sgr, then I'll be able to make this turn. Okay, so because the maximum friction is good enough to balance. If the velocity is less than that, then it is pretty obvious we'll be able to make that turn because this is the maximum friction that I found over here, right? If the frictional force that is required is less than that, then obviously the ground will be able to provide that much amount of friction. Therefore, I'll be able to make that turn. Okay, so that's not a problem. If the velocity was greater than root of mu sgr, in that situation I'll not be able to make that turn. I need like some component to increase. Okay, so if that was the case, mu s is the coefficient of friction between the tire and the road that cannot be changed. It will be like a constant one. G is the acceleration due to gravity, that is constant for the earth. So only parameter which I could vary is the radius. Okay, so if I come with more velocity than the optimal velocity, in that situation radius is the only thing that could change. Therefore, I need a bigger radius to make that particular turn with that particular speed, right? So you should be clear with the concepts that I've told you over here. You shouldn't have any doubt. So in this case, I just saw car taking a turn on a level road. So next we will see like car taking a turn on a banked road. Okay, so banked road actually means inclined road. Fine. So we'll see that one in the next page, right? Next, we will see like motion of car on a banked road. Fine. So banked road actually means you're having an inclination in the road. Fine. So that inclination will also be helpful for the turn of the car. Okay. Right. So you're having an inclination in this case with respect to the left. Okay. So the inclination is towards the left. So that's how I've made the inclination. Obviously, the car is going to make a turn towards the left. Okay. If I have to make the inclination towards the right, if that was the case, then the car is going to turn towards the right. Fine. So that's how I'll make the inclination in the road, right? You might have seen in the fast track highways. Okay, so when they are just designing that highways, obviously if the turn is towards the right, the inclination will be towards the right because that right inclination will be helpful for the car to make the turn towards the right. Okay, so obviously when a road is banked, I'll be able to make the turn with greater velocity when compared to that of the horizontal road, right? So that thing is possible. That's why I'm just going to make this inclination. Fine. So banked road actually means inclined road. So though the road is at certain inclination to that of the ground, so that's what banked road represents. Fine. So here the vehicle is going to turn towards the left. Obviously the inclination is also towards the left, right? Okay, so here I just need to put in those forces and then I'll have to balance those equation, right? So if I just end up getting those equation, I'll be able to get the velocity, maximum velocity with which I'll be able to make the turn. Okay, so here obviously this inclination will also be helpful for the centripetal force. Same way the frictional force that is acting between the tire will also be helpful for that particular turn. Okay, so in this case the car is going to turn towards the left, right? So generally when I take the coordinates, I will always take with respect to the inclined plane, right? So along the inclined plane, I'll just take the x, and then perpendicular to the inclined plane will be like y. So this is how I'll take in majority of the situation, right? So while doing PVQ, in 99% of percentage of the cases, I'll take it in this fashion, okay? In like complete, in all the situation, I'll just take it in this fashion, which means the x will be along the y, and then the x will be along the inclined plane and y will be perpendicular to the plane. But in this theory part, where we are going to derive some certain equation, right? So it will be convenient if I take it in the normal way with respect to the ground. So x will be along the ground and then y will be perpendicular to it. Even if you take it along the inclination, you will end up getting the same result. The reason why I have took it in such fashion is because while doing it in this fashion, it will be easy to get the final result. That's it, right? But while doing sums, do not want to confuse. In 99% of the cases, always I'll take like inclined plane to be my x and the perpendicular to the inclined plane will be like y, okay? But in this case, I'm just going to take it other way around for like easy solving. That's it, nothing more to it, right? Okay, so here I'll just have to plug in extra forces that are acting on this body, which means I'll have to do the free body diagram for this particular body. Then I'll just solve the component that is along the x and that is along the y, right? So I'll end up getting 2n when I equate those two normal forces, which is like the same thing, but got for the forces along the y and then for forces along the x. So I'll end up getting two normal forces, and then when I do equate those two things, I'll get the maximum velocity with which I could make a turn for this particular bank road. I'll be able to get that answer, right? Okay, so that's what I'll have to deduce from this thing. Okay, so here let me explain you the picture. So you have got a car that is going to make a turn along the left. The road is also banked along the left. Okay, it is inclined towards the left. Okay, so the mg, it is actually acting downwards, right? So mg will always be the same. It will act on its center and then towards the down. Okay, so that will be like mg, gravitational force. Okay, so then you have got the normal reaction, right? So the normal reaction will always be perpendicular to this surface, right? So normal will be like perpendicular to this inclined plane. So that will be my normal reaction, right? So these two things are done. Now let me put the frictional force and all those things, and I'll do the rest all other solving. Okay, so to match the theta, you should know that one, right? So this theta should be equal to that of this one, right? So this line is actually perpendicular to the horizontal, and same way this one is perpendicular to the inclined one. And if this was my theta, then obviously this will be my theta, right? So these two things are done, right? So then the rest components will be like the split that I've made over here. So if this was like the normal, then opposite component will be the normal force, right? So this will be my normal force, and then I've just drawn one component over here. So I'll split this normal into two stuff. Okay, one will be like n cosine theta and the other one will be like n sine theta. So if I do like resolution of vector for this normal component, you'll have like one component, right? N cosine theta and then the sine theta. So I should know the theta, right? So here if I have to match these two thetas, obviously this one and this one are intersecting each other. Therefore these two angles are like same, opposite angles will be like same, right? So these two things are same, so this will be my theta, right? So these are the things that you know, that you need to know as if now regarding this diagram. You should be clear. Now I'm just going to put in extra forces that are acting on this object. Okay, so the extra one force will be like the frictional force, right? Obviously. So how does the frictional force will act on this object? It has to turn towards the left, right? So if this object has to turn towards the left, obviously I need a centripetal force that should act along minus x axis. Okay, so as the centripetal needs to be acted towards the left, obviously friction should also act downwards. Okay, so that is when this frictional force will constitute extra force that will be responsible for the required frictional force that is needed, right? Okay, so here frictional force will be acting downwards. If this car was at rest in this banked road, then in that case frictional force will act upwards because it will slide downwards. Therefore, frictional force will act upwards. But in this situation, I just have to make a turn towards the left. Okay, then I need force towards the origin. Okay, so in this case, towards the origin or radially inwards. If that was the case, then obviously the frictional force should act downwards. So that one component of that frictional force will be responsible for the centripetal force that is needed, right? So that should be clear. Therefore, in this case, you will have a frictional force that is acting downwards. So this will be my frictional force, right? So I've just put it over here. Okay, so now let us get the theta for this particular frictional force. Okay, so I'll have to match another one theta to it. Okay, that is same as that of this theta. Okay, so to match that one, I have just drawn this one more time over here. Okay, so or else this will become clumsy. So you're having a frictional force that is acting downwards, right? So what should be my theta? That's what I need to get over here. So you are having a frictional force that is acting along the inclined plane. And then if I do resolve this vector into two components, you'll have like one component that will be parallel to that of the mg, and the other one will be like this one. So that will be responsible for the centripetal force. Okay, so one will be like parallel to mg and the other one will be like parallel to this centripetal force. Okay, so that's how I'll have to split this frictional force, right? So that's what I've drawn over here. So you're having like frictional force, one is acting downwards and the other one is like perpendicular to it. So which should be my theta? That's what I need to find, right? So here also I'll have to take like two right angles, and then if I match it, I'll end up getting it. So one will be like this one, right? So this one will be like one splitting. So this will be like one, where this is my theta, right? So this component, you are having theta over here, and then the other splitting will be like this one. Okay, so these two angles are at right angles to each other, right? So one is this one and the other one, here you have the friction, and this was my theta. So if this was my theta, then obviously the other one over here, so this should also be the theta, right? Because when those two angles are like on top of each other, you don't have any theta formed. Then what I did is I just started inclining one of the angle over there, so you just got like one more extra theta swept or above the surface, right? So obviously you will have like theta formed over here. The theta formed over here will be same as that of the theta that was formed over here, right? So this is something that we have already seen. You should be clear with this one, right? So here the theta, so you have got like two right angles in this fashion. One is like this one and the other one is like this one. If this was like theta, then obviously this should be my theta, right? You should be clear. So here the theta will be this one. So this was my theta. If this was my theta, then the component that is close to theta will be like f cosine theta. So this will be like f cosine theta, and this one will be like f sine theta. Okay, so now I have got those two components into it. So when I do split these two things, I'll have something like this. You will have like f sine theta that's going to act downwards, and then you'll have one more component which will be like f cosine theta. So f cosine theta will be responsible for the required centripetal force. Okay, so that will be assisting in the centripetal force. Okay, so then you have got this like n component. I'm going to split this one with respect to the y and then the minus x axis. So with respect to y axis, you'll have like theta close to it, so that component will be like n cosine theta. Okay, so now I'm just almost done with the resolution of vectors. So you'll have like n cosine theta, that will be like perpendicular, and then you'll have one more component which will be like n sine theta. So here, because of that inclination of the road, you have got this thing n sine theta, which is also responsible for the circular motion, which is responsible for that circular motion of the car. Okay, so now we have got like two component, one will be like n sine theta and the other one will be like f cosine theta. So these two things will assist in the circular motion of the car. So those two things will be helpful for the centripetal force in this situation. Okay, so that is why I have banked the road, right? Got it? Now I'm just done. So let us do the summation of forces along the y, and then I'll end up getting one n component. Okay, same way if I do like summation of forces along the x, I'll also end up getting one more n component. When I do equate these two n, which are the same normal, which is the same normal force, because we have just got the same equation and put it in two different axis. That's it. That's what we have done over here. When we get those two n by equating summation of f of y and f of x, we'll get the maximum velocity with which I'll be able to make the turn. Okay, right? You should be clear. Now let me equate the forces along the y. Okay, so what is the summation of force along the y? So here if you look, it is pretty obvious. The car isn't going to break the road and it is going to move downwards. Okay, so obviously the force along the way, summation of force along the way has to be 0, because the car isn't breaking the road and it is moving downwards, right? Along that inclination, that's not going to happen. Therefore summation of force along the way should be equal to 0, right? So the first thing is set, which is like summation of force along the y is equal to 0. Next, let me equate those forces that is along the y direction. So you're having like n cosine theta that is acting upwards. Therefore, you will have n cosine theta, which is like acting upwards, that will be like j cap, and then you will have two components which is actually acting downwards, that will be like mg and then f sine theta. So you will have like plus mg, which will be minus j cap because it is acting downwards. Same way you will have like f sine theta, then you have like minus j cap, which is acting downwards. Okay, so summation of forces along the y should be equal to 0, therefore your right hand side will be like 0. This equates to 0. Now I have got this one. So the thing that I'm going to find from this equation is the n, right? So if I have to get the n, what I should do, I'll have to put n on the left hand side, rest all other components will go to the right hand side, right? So if I do that thing, you'll have n cosine theta, and then mg will go to the right hand side, so you'll have like mg. So instead of frictional force F, I'll just replace it with obviously mu s n, right? So it will be replaced by mu s n sine theta. Okay, so here instead of plus you will have like negative sign. Got it? Because you've got like f sine theta minus j cap, therefore for frictional force I just substituted like n mu s n sine theta, right? Obviously even in this situation, this is like a static case. Okay, the car isn't sliding downwards, therefore frictional force will be the static friction, right? Okay, or else the car isn't moving upwards, whatever it is like static with respect to the inclination, therefore this should be like static friction, which is like mu s n. If I just factor out n in this case, so I'll just end up getting the equation that is needed. So if I just factor out n and then I just put the entire term in the denominator, I'll get this stuff. So we will have the next step will be like factor out the n. So n, you'll have like cosine theta minus mu s mg, cosine theta minus mu s sine theta, which is equal to mg. So this is what you'll end up getting. So for n normal force, you'll have mg divided by cosine theta minus mu s sine theta. This is what you'll end up getting. Alright. So now I have got the normal reaction by equating the forces along the y. So when you do equate forces along the y, the summation of those forces will be like 0. So now I have got the first n by equating the forces along the y. Next, what I'm going to do is I'm just going to equate the forces along the x. So here in this situation, it is clear you do not have any forces that is acting along the plus x. There are like two components which is acting along the minus x direction, right? Obviously these two things are responsible for the centripetal force, right? So when you do add these two things, it will not be equal to 0, right? Because this will be responsible for the circular motion of the car. Therefore when you do add these two forces, it should actually equate to the centripetal force, right? So that will be the maximum velocity with which I could make the turn. If my velocity was less than that, that will be easy for the car to make a turn, because obviously frictional force is a variable thing. Okay, accordingly the frictional force will get reduced. Fine. So anyway, so here what I'm actually finding is the maximum velocity with which I could make a turn. Okay, if the velocity was less, then no problem, frictional force will adjust itself accordingly. But the n sine theta will not be able to change that component, because n sine theta has been generated because of mg. So you will have the same weight that is acting, and the inclination is also going to be the same thing, right? So that thing could not be controlled, but the thing is friction will change accordingly. Here what I'm finding out is the maximum velocity or the maximum possible situation with which I could make that turn. Okay, so here it is pretty obvious, summation of forces along the x is not equal to 0. This logic should be clear, because these two forces are responsible for the frictional force. So summation of force of these two things will be equal to mv square by r. That will be equal to the frictional force. Okay, so even in the last situation, that's how I framed that equation, right? Frictional force between the rod and the tire was equal to the centripetal force. Same way here, the x component minus x component will be equal to the centripetal force. Got it? It should be clear. So here summation of force along the x is not equal to 0. It is actually equal to the centripetal force. So the centripetal force over here is m v square divided by r. You should put the direction clearly, because I'm just involving two parameters, I and then the j. So here it is like minus I cap. It is acting towards the negative I cap. Yeah, so that's how it should actually act. Okay, so I could either put like r cap or minus I cap, whatever it is, okay. If I just consider it to be like radial direction, in that situation I'll put like negative r cap. So negative r cap means it is acting radially inwards. So you should be clear with this idea. So here the negative r cap is nothing but the minus I cap, right? So I have just put in straight away. So that will be like summation of forces along the x, which will be equal to mv square by r minus I cap, right? Now I'm ready to put in those two forces that is acting along the x-axis, right? So there are like only two forces that is acting along the x-axis, which will be like n sine theta minus I cap, and then you'll have like f cosine theta minus I cap. So if I just put those two things, so two component that is acting over here is like n sine theta, which will be like minus I cap. Got it? It should be clear. So you'll have like n sine theta that will be acting along minus I cap direction. Same way you'll have f cosine theta that too will act along minus I cap direction. Okay. N sine theta minus I cap, and then you will have plus f cosine theta minus I cap, which will be equal to m v square divided by r minus I cap, right? So now I have framed this equation the same way. If I rearrange this one, I'll end up getting this n component, okay? So instead of f, I'll just substitute like mu s n, and then I'll factor out this n from this equation. If I just do the rearrangement thing, I'll end up getting the n component, okay? So once I've got the n component because of summation of forces along the x, I'll be able to equate this first equation with the second equation that I'm just going to get, okay? So here if you look into this equation, obviously these negatives will become positive, so only thing that will be left with the is the positive term. Just do the rearrangement thing, you'll get the answer, right? So let's do the rearrangement in the next page. First I've got like n sine theta minus I cap, right? So let us remove those negative sign because obviously it will get cancelled. So you'll have like n sine theta plus the next component will be like f cosine theta minus I cap, right? So instead of f, I'll substitute like mu s n. So you'll have like mu s capital N cosine theta, which was equal to mv square by r. Okay, so you'll have like mv square by r, right? So now if I just factor out this n, okay, I'll get the capital N that is needed over here. Now if I just factor out that n, I'll end up getting the n that is needed, okay? So let us do the factoring out stuff. We'll have n, which will be equal to sine theta plus mu s cosine theta, which was equal to mv square by r, right? So now the last step is n, which is equal to mv square divided by r. You will have like sine theta plus mu s cosine theta, okay? So that's what you'll get for this particular n, okay? So now I have got like two n's, right? So then, as I've already told you, we will have to equate those two equations. So the first thing is like mg divided by cosine theta minus mu s sine theta, right? So that was the first equation that I've got. Same way, the next part will be like mv square by r, the above one. So I've put that one straight away here. So the term that is same in these two equations is like m. So I'll just cancel out those two, m, okay? So now if I do the rearrangement thing with respect to the velocity, because the velocity is something that I'm going to get, right? So if I do the rearrangement thing, you will have like v square. Obviously, this is the maximum velocity with which I'll have to make the turn. If the velocity was less, then I'll be able to make the turn. Friction will adjust it accordingly. So here, if I do the rearrangement thing, you'll have like r mu s cosine theta plus sine theta divided by or mu s cosine theta plus sine theta divided by, you will have cosine theta minus mu s sine theta, right? So same way you need to have like g in the numerator, right? So you're just having one more g over there. So that is something you'll have in the numerator, okay? So now I have got this bigger term. So let's do some trigonometric thing into it, okay? And then I'll just simplify this equation. So when you look at this equation, what I'm going to do is I'll just multiply in the numerator by 1 by cosine theta. Same way I'll do the same multiplication in the denominator by 1 by cosine theta, okay? So in the numerator, you'll have like 1 divided by cosine theta divided by, you'll have like 1 divided by cosine theta. Therefore, this term isn't going to change. It's obvious, right? You shouldn't have any confusion. So when I do the internal multiplication, what will happen? You'll have like RG, that's going to be same. You'll have like mu s cosine theta divided by cosine theta. So that thing will be like mu s. And in the second case, it will be like plus sine by cosine theta. That will be like tangent theta. Okay. So the numerator over here will be like will be R G. That will be the same. And then you'll have mu s cosine will get cancelled out. And then you'll have like plus tangent theta. Okay. And in the denominator, when you do the inner multiplication, you'll have like cosine theta, those two things will get cancelled out, and then you'll have like 1 minus mu s, 1 minus mu s tangent theta. That's what you're going to get, right? So now now I have got the maximum velocity with which I could make a turn, which will be like root of rg mu s plus tangent theta divided by, you'll have to remember this big formula, okay? It will be handy while doing the PVQ. So this is one of the formula that you will have to memorize it, okay? Rg mu s plus tangent theta divided by 1 minus mu s tangent theta. So now I have got this maximum velocity with which I will have to make a turn, okay? So this stuff is done. Then I'm just going to take a special case, okay? So even I've already told you that banking should be helpful for the turn, right? So even if there wasn't any friction between the road and the tire, still I should be able to make the turn, right? If that was the case, which means there isn't any friction that is between the road and the tire, which means this friction is not acting. Even in that case, I should be able to make the turn. If that's supposed to be the case, then frictional force, if frictional force was equal to 0, then with what maximum velocity I could actually make a turn. That's what I need to find. So if that was the case, then obviously when f was 0, then you shouldn't have any mu s. Obviously there isn't any friction, then mu s should also be equal to 0. So if that was the case, then mu s should be equal to 0. So this term goes to 0. Same way in the denominator, this mu s, this term goes to 0. So when those two terms goes to 0, maximum velocity Vmax will be equal to root of RG tangent theta. Okay, so that will be the component that is responsible for the circular motion. Okay, so if the velocity was equal to root of RG tangent theta, then in that situation still I'll be able to make the turn even if there isn't any friction between the road and the tire. Okay, so here it is pretty obvious that banking is helpful for the car to make a turn. Okay, so even if the velocity was greater than the optimal velocity with respect to the horizontal road, still we'll be able to make the turn in the banked road because that inclination is helpful. Okay, so you should be clear with the stuff that we have seen over here. Same way, you should remember this bigger formula. Okay, so this formula will be handy while doing the PYQ. Therefore, you should memorize this one. Obviously, if you do memorize this one is like super easy. Just put 0, you'll end up getting the maximum velocity if the case was friction equal to 0. Okay, this should be clear. So with this, all the theory part that are related to laws of motion gets completed. Only thing that is left is the extras part, which will take around 20 minutes. We'll do that one also, right? So you should be clear with this stuff. The next step, the next thing that we are going to see is like contact forces. That's a kind of extra stuff that we are going to see. Okay. Next one is contact forces, right? So if you're just clear with the idea of contact forces, then tension in rope will automatically fall. Okay. So first, let us see what is meant by contact forces. Okay, so this is a kind of same logic, but the thing is the contact force acts between two surfaces. Okay, so between the contact, if the force is acting, then that is called as contact forces. Okay, so everything rest, all other understanding is just the same thing. Okay, so we'll do free body diagram for these three bodies separately, and we will see how does the force act in this contact. Okay, so it is just the same force. Only thing is, I'm just going to find that particular force on the contacts. Fine. Okay, so rest all other understanding is just the same thing, right? So this logic will be helpful in the PVQs. While solving PVQ, I do not want to teach this one again. Okay, so if you just know this idea clearly, then while doing the PVQ it becomes easy, right? Okay, so here let us consider this way. You have got like 10 kg separated in this fashion. One is like 5 kg, 3 kg, and then 2 kg. Okay, so I'm just going to give a 10 Newton force to this entire object. Okay, so for to this complete mass, I'm just going to give a force of 10 Newton. I've just taken it in a fancier way so that it becomes easy for us to calculate. Okay, do not want to worry about the numbers and multiplication, those stuff. Okay, so here I'm just going to give 10 Newton and the mass that is over here is like 10 kg, right? So with what force, with what acceleration this is going to move? That's what I need to find first, okay? So to get that one, I know the total mass and I know the force that I'm giving on it towards the right, okay? Those two things are known, okay? Then obviously, if I do a little bit of math, you'll get the answer. So F net was equal to 10 Newton, okay? So F net was equal to 10 Newton. So instead of this force, I'll substitute like mass and then the acceleration. So you have got like m, and then a net acceleration will be equal to 10, okay? So for the mass, I'm just going to put in this entire mass because I'm going to calculate the entire acceleration of this entire system, okay? So a net will be the acceleration of this particular system, which will be like 10 kg. So you will have like 10 substituted for m, and then a net which will be equal to 10. So you'll have like 10 will get cancelled out. Obviously a net will be equal to 1 meter per second square, which means if I continuously give a force of 10 Newton on this 10 kg mass, this will undergo an acceleration of 1 meter per second square, which means at every 1 second the velocity is going to increase by a factor of 1, okay? I mean, it's going to increase by 1 meter per second, fine? So the acceleration that I've got over here was equal to 1 meter per second square. So 1 meter per second square was the acceleration that I've got over here, okay? So now I'm ready to find the contact forces. So what is the force that is acting on this 5 kg mass because of this contact, okay? Obviously this 5 kg pushes the 3 kg forward, 3 and 2 kg forward. In turn, this will experience a backward force, right? So what is that forces that is acting on this contact? That's what I need to get, okay? So let me take the contact force in the first situation as F1, okay? So you are going to have force F1 given by this 3 2 kg setup for backward, which will be equal to F1, okay? So you will have the same amount of force applied by this 5 kg on these two objects that is in front of this 5 kg, okay? So that will also be the same amount, right? Because the forces are equivalent and opposite. So you'll have like F1 that will be acting forward, okay? So this F1 will be responsible for the acceleration of this 3 and 2 kg mass, okay? So because of this F1 force, there will be a contact force that is generated. You could split like infinite times in between, but the thing is I've just chosen like two different contacts. That's it, finished, okay? So if I just consider this contact, then in that situation, obviously you are having a force F1 that assists these two masses to move forward, okay? So because of that one, this 2 kg will receive a force that is going to push it forward, and then it will generate an acceleration of 1 meter per second square. Therefore, you will have an force that is pushing this F2 mass, this 2 kg mass forward. That force will be like F2 that will act towards the plus x-axis, and then in turn it will push this entire system backwards by a negative force of F2, okay? So here in this case I didn't put like positive and negative sign because while doing the mathematical stuff I'll just put in those plus and then negative sign, okay? So now I have just put in the contact forces. So contact forces is just a simple one, right? So you just have to pick that contact, and then whatever force that I put forward, the same will be acting backwards, okay? Because we know obviously every force has an equal and opposite reaction, okay? So here for this 5 kg mass, let me do the free body diagram and force balancing stuff, okay? So free body diagram is already done. So F1 is acting towards the minus x, and then you are going to have a 10 Newton force that is going to act along the plus x direction, okay? So if I do solve this one, you have like 10 which is acting backwards. I mean, which is acting towards the plus x-axis, and then F1 is actually acting towards the negative. So minus F1, that is going to give an acceleration of 1 meter per second square on this all those objects, okay? So first object will also have an acceleration of 1 meter per second square. So the mass of that object will be like 5, and the acceleration will be like equal to 1 meter per second square, right? So F1 over here will be like, if I do the rearrangement thing, you'll have like 10 minus 5. That's what you'll end up getting. Therefore, F1 will be equal to 5 Newton. So here, I just put in the negative direction properly, right? Therefore, I just got the answer to be like 5 Newton, which means the force F1 is acting backwards with a magnitude of 5 Newton, okay? So 5 into 1 meter per second square was also towards the plus x-axis. Therefore, I just put it positive itself, okay? So F1 will be like 5 Newton that will be acting in that particular contact, okay? So here it is pretty obvious you are going to have a F1 force of 5 Newton that is going to act backwards, and then here I'm just going to push it with a forward force of 10 Newton with leftover 5 Newton force. This will get accelerated by an acceleration of 1 meter per second squared. So this first thing is done. So for the second object, which means the in between one, for the middle one, if I consider, what you will have is this 5 Newton forward force will be acting because this entire system pushed it backwards by a force of 5 Newton. In turn, this second part of the system would have received a force of 5 Newton. Okay, so obviously you will have like F2 that will act backwards, that will be responsible for the motion of the second 2 kg mass. Okay, the third mass. So free body diagram for this in between mass is done. So let me do the force balancing stuff. So if I do the force balancing thing, you will have like F1 that is acting towards the positive direction, and then you will have like minus F2 that will give me 3 into 1, right? So F1 minus F2 will give you like 3 into 1, which means one is like acceleration 1 meter per second square. So here I've already got the force F1, okay, which is like 5. So you have got like 5 minus, you've got like 5 minus F2, which will be equal to 3, right? So F2 will be equal to 2 Newton. So now I have got the F2, which was equal to 2 Newton. F2 was equal to 2 Newton. So this thing is done, right? So here I've put the direction properly. It is acting negative, therefore I just got the answer to be in positive direction, positive value. Okay, so the magnitude is something that I've got over here because I already know the force F2 is acting along the negative direction. Same logic that I've told you over here with respect to the force F1, right? Next we can verify it for the third mass. So the only force that is acting on the third mass is just the F2. Okay, so left hand side will be like 2. Yeah, obviously that will be equal to 2. Yeah, right hand side will be the mass times the acceleration, so that will be like 2 into 1. Obviously these two things are the same thing. So if I have a force of 2 Newton acting on this 2 kg mass, obviously this will have an acceleration of 1 meter per second square. So here the entire system had an acceleration of 1 meter per second square. That thing is something easy for us to find. What I've just found over here is what will be the forces that is acting equally and opposite on the contacts. That's what I found over here. Okay, the first contact I had a contact force of 5 Newton. So that 5 Newton one was responsible for decreasing the force on the first object, and then with respect to the rest two other bodies it was responsible for the forward acceleration. Okay, so that's how it got split in this particular contact. So same thing happened in the case of the second surface. Okay, so now we should be clear with the contact forces. Okay, so contact forces is just the same thing that we have learned already. Okay, so it is just the same force, but the thing is I'm just going to study it in the contact. Okay, so in the contact you will have like equal and then the opposite reaction. So how did that reaction actually act on that particular contact? That's what we did see over here, right? If you're clear with this particular stuff of contact forces, then tension is something easy for us to understand. Okay, so next we will see tension in rope or string. So that will be the final part for this session. So with that, the session will get completed. Okay, now we will see tension in rope or string. Okay, so first let us take an easy situation. Okay, so which means in the static condition how does it actually behaves. Okay, so once you are clear with that one, then obviously it will be easy for us to solve with the masses. Okay, so it will become easy, right? Okay, so first I'll take simple situation. Here you have got like a thread or a string which is stretched by the same amount of force on both those sides, which means on the right I'm just going to give a force of like 5 Newton. I've just taken it in such a fashion. Same way the other end, let us consider it is tied. Okay, so obviously even in this side you are going to have a force of 5 Newton, which means in this situation this string isn't going to move. Okay, so on both those sides you are going to have like same amount of force, which means it is just going to get stretched, it is not going to move. Okay, forces is going to balance each other, right? So let us see how does this force actually gets balanced, right? In this situation I'll just consider like three molecules or atoms. Okay, so I'll just study those three atoms. So you are going to have like infinite number of atoms, obviously n number of atoms, so that will be the behavior for all those n number of atoms. Okay, so if I just clear with this three atoms and then the forces that is acting opposite to each other, right? Once you're clear with that one, even if you're going to have like millions of atoms, same thing is going to happen for those millions of atoms. Okay, so here I've got like three masses, 1 2 3. Okay, I'm just going to consider like three atoms. Fine. So initially it was unstretched, which means initially I didn't give any external force to it. So that in that case it was like unstretched. Then I have given two 5 Newton forces opposing to each other. Okay, on one side I'm just pulling it by a force of 5 Newton. Same way on the other side I'm just pulling it by a force of 5 Newton. So in that situation the atoms just got rearranged. Okay, it is not going to break. If it was going to break, then obviously you will have like force that is acting. Okay, which means you are going to have an acceleration, but in this situation it just got stretched and it became static. So if that was the case, then this 5 Newton force has to be balanced even on the atoms that is inside of it, right? So here on the left you will have a force of 5 Newton. So if you do not have any 5 Newtons acting towards the right, obviously this will tear apart and it will just come out, right? But instead what is happening over here is you are having like interatomic forces. Okay, between those two atoms you will have like interatomic forces or van der Waals force that is responsible, bond that is responsible for that atoms to stay together. Okay, so then what we'll do is, so the electron cloud on this atom is going to attract this proton. So obviously when it moves away from the mean position, so this thing will attract. So this atom, the next atom will just give an inward pull of 5 Newton. So that is pretty obvious, right? So the atom next to it will give inward pull of 5 Newton. So that will be given to this first atom. So what will happen to the second atom? So in turn, because it has given an inward pull, so I'm going to pull that one inside. So obviously I will experience a force towards the right. Okay, so I'll have like counter effect on me. So I'll experience that force which will push me towards the left by a force of 5 Newton. Okay, so this thing pulled this one backwards with a force of 5 Newton. In turn I got pushed forward by a force of 5 Newton. Okay, so it should be clear. Then so this setup has to move front, so this atom has to move towards the left with the force of 5 Newton. So what will the next atom do? So the next atom will obviously pull this one backwards with the force of 5 Newton. So same thing is going to repeat, right? So it will pull this one backwards with the force of 5 Newton. So this atom actually pulled this atom, the atom that is ahead of that one, by a force of 5 Newton. Then obviously this thing will also get pulled forward by a force of 5 Newton. Okay, so this thing will keep on repeating until it comes, even if you have like millions of atoms in between it, in between this rope, what will happen is this thing will keep on repeating, and on the final point where I have given a force of 5 Newton on the other side, okay, so it will just keep on repeating until this point comes, right? So obviously this 5 Newton is going to balance this 5 Newton. So this 5 Newton has actually balanced the 5 Newton that is on the other end of the rope. Okay, so 5 Newton will get in balanced inside, and when you look at the other side, you will end up having this 5 Newton, right? So here, when this string or thread is static, which actually means I'm just going to give same amount of force on the two ends of the string, which means even every atom that is inside that string will also experience that 5 Newton force, and it will just rearrange its positions, and then the entire system will become static. Okay, so that's what I just intended to tell you. Okay, you should be able to understand that everything that I've told you over here, right? You shouldn't have any doubt. So the same thing, I'm just written a statement over here. When the object is static, it doesn't matter it is string or any other solid object. When the object is static, it simply means internal forces are balancing each other. Okay, so internal forces cancel each other. Okay, so even if you don't give any external forces, still you have like proton electron attraction, all those things happen inside that atom. So all those things will get balanced each other, and you do not have any net force because of that internal forces. Okay, that is when the object will be static. So that's the statement that I have written over here. When the object is static, it simply means internal forces are cancelling each other. Okay, so internal forces will cancel each other. Internal forces cancels each other. Right? You should be clear with this statement. Now, I'll just give an understanding the same way that you have seen for the contact forces. Here you have got like two masses, right? Here you have got like two masses. One is like 3 kg, and then you have got like 5 kg. Obviously, I'm going to pull it forward by a force of 5 Newton. So with what acceleration this entire system is going to move, that is easy for us to understand. Okay, so here it is pretty obvious. I'm just going to give a force along one direction, which means this entire system is going to accelerate. Okay, so if that was the case, then force F net will be equal to 5 Newton. right? So instead of F net, I'll be able to substitute like mass times the acceleration. So for the mass, I'll have to add the entire setup, which will be like 5 kg. So 5 into acceleration is something that I need to find. A net is something that I need to find, which will be equal to 5. Therefore, acceleration will be equal to 1 meter per second square, which means this entire system is going to accelerate towards the right with an acceleration of 1 meter per second square, right? You've got this one. Okay. So now what I'm actually intending to find is what will be the tension that is acting on this rope. We obviously know when you're going to pull something forward, that rope is going to pull this uh, object A towards the forward. Okay. So obviously you are going to have a tension that is acting on this rope. So the rope will get stretched because of the tension force that is acting, right? So here let me consider the rope to be massless, okay, which means the mass of the rope is infinitely small, which means negligibly small when compared to this 5 kg. If that was the case, then how should the tension actually act on this mass? That's what I need to find. How should the tension actually act on this rope? That's what I need to find. Okay, so to get that tension, what I'm going to do is I'm just going to do a free body diagram for this mass A and then the mass B. Okay, so for mass B, obviously this 5 Newton will not completely act on this mass B because some part of this force should be responsible for the motion of the object A. Okay, so how will the force actually transfer to the mass A is because of this string. Tension of the string will be responsible for the transfer of that particular force to this mass A. Okay, so obviously you will have a tension force that is going to pull this mass A forward. Okay, in turn by the same amount, this mass B will be pulled back by the same amount of tension. Okay, so obviously you are going to have a tension in the string. One part of the tension will pull the mass A forward and the other one will like pull the mass B backwards. So if you look at this force, it is pretty obvious these two tension are just the same thing, which means I'm just putting this arrow mark in this fashion. One side you are going to have a tension towards the left, on the other side you'll have a tension towards the right. Okay, so obviously this string will get stretched and then and then obviously you are going to have an acceleration, but the mass is negligible. Okay, therefore this thing will get stretched. That's it. Fine. You will not have any forces that is actually used for the rope because the mass of the rope is negligible. Okay, you are having acceleration, then you should obviously have like decrement in the tensions. Fine, but the thing is I've just considered here like mass to be negligible, therefore this tension will be like same for the mass A and then the mass B because the acceleration that got generated in the rope is like zero because the mass in itself is negligible. Therefore I equated the mass to zero. So whenever you just do the contact forces, what you do the how you actually do the multiplication is mass times the acceleration. In all those situations you had like mass and you got like some acceleration, but if this entire system was at rest, then acceleration will be like zero. So that was the case over here. Therefore all those forces got balanced. In the situation you are going to have acceleration, this entire system is going to get accelerated, therefore the rope will also get accelerated. But the thing is I just considered the mass to be negligible, therefore when you put like ma, obviously m is going to be zero. Therefore even if you have like mass, it seems to be pretty obvious the tension will not be decreased in the situation because the mass is negligible, right? Therefore that entire equation goes to zero, right? You should be clear with the stuff that I'm telling you. So here you're going to have a tension that is going to act backwards, that's going to pull this one backwards. It will not give like entire 5 Newton for the mass B. Some of that forces will help for the mass A to move, accelerate forward. Okay, so the tension will obviously act backwards, right? We consider here obviously one part of the end is actually pulled towards the right and the other part of the string is actually pulled towards the left. So these two things got balanced, therefore tension will be same on this stretched string. Okay, the thing is this string will be stretched. Okay, you should get that idea. And then for the mass A you will have a tension that is going to act towards the right. Fine, so now this part is done. Fine, so these two t are just the same thing. So if you just do the equation for the second object only for the mass B, obviously this thing will just automatically come because this tension and this tension is just the same one. Okay, so if we do it for this one, you'll have like 5 Newton that is acting towards the right, so that's going to be like 5. minus t, which will give me like mass times the acceleration, right? So the mass over here is like 2 and the acceleration over here is like 1. Okay, so 5 minus t will be equal to 2. So T will be equal to, if you do the rearrangement, you'll end up getting 3 Newton. Okay, so you're going to have a backward tension force that has been generated because of the rope, which will be equal to 3 Newton. Okay, now I have got the tension. So this tension 3 Newton, it is pulling the mass B backwards. Okay, why does this one get generated is because of the mass A, which wants to move forward with the help of 3 Newton force. Okay, then obviously this will pull the object that is front backward by a force of 3 Newton. So here this is going to experience a tension, this is going to experience a force of 3 Newton forward because of the tension in the rope. Okay, so obviously even if you do force balance here, you'll end up getting the same result, which is like 3, that is acting towards the right, which is equal to mass times the acceleration. 3 into acceleration should be like 1. Okay, so obviously 3 will be equal to 3, right? So this thing is done. So the only difference between the first example and the second example is here I'm just going to push it from the back. Okay, from the left to the right. Okay, from the back side. Here I'm just going to pull it from the front because I have attached a rope over here. So instead of contact forces, this tension was responsible for the motion of those two objects. Okay, so you should be clear. So this tension is also similar to that of the contact forces that we have already seen, because it is pretty obvious these two tension are actually acting equal and opposite. It shouldn't be equal and opposite in every single situation, but the thing is here, when compared to that mass, the mass of the string was actually extremely low. Okay, that's why I considered the mass to be 0. Therefore, even if it got accelerated, those two, when you consider those two ends, you end up having the same tension. Okay, so you'll have to imagine this one same as that of the contact forces. Okay, so even if they have given you like contact forces or they give you rope, whatever the case it is, the tension in the string or contact forces will be like equal and opposite to each other. Okay, so that's the final verdict that you need to know, right? So you should be clear with the stuff that you've discussed over here. So this is a kind of extra part which you should be clear. Same way we did see the motion of car on a banquet road and on a circular track. So you should know that big formula that I've told you with the case of motion of a banquet road. So you should remember that entire formula. And then motion of a car on a circular track is super easy. Okay, so that thing should also be known, right? So with this, everything that is related to this chapter got completed. You should be clear with all the concepts that I've told you, right? So with this, the video gets completed. Bye.